So what we just got is basically the number of states between k and k plus dk, okay, where k is the magnitude of the momentum. Okay, so you think about electrons having momentum k and momentum k plus dk. Okay, k is some number, some value of momentum, and plus dk. So if you increase it, the momentum by some limit dk, how many number of states are there between. So, or with respect to the energy band also you can talk about this. So if you have a band like this, and suppose you are here, you are k, and you go by k plus dk. Okay, so this is your dk. So in this, how many different how many different k values or how many different states are there? So that is what we are counting in a 3D space. Okay, we are considering a 3D space. And one of the thing I have not mentioned is that for each k value you can have, or for each energy state you can have two or you can say the electron can have two different spins. Spin I have not yet talked about. So if you include the spin, that is like in each of the state, which is determined by a k, this one of the point here, one of the state here, you can have electron with up spin or down spin. Okay, so these are this is an additional degree of freedom which we have not considered in the Schrodinger equation. So that is another aspect of quantum mechanics, that electron also comes with a spin, and therefore each orbital, say s orbital, you can put two electrons in it, one with a down spin and one with up spin. Similarly, px orbital, you can put two electrons there, not one electron, although it is one spatial state, but two electrons can be put in there because of this is called spin degeneracy. So including spin degeneracy, g of k into dk. So this is the number of states in the k space between with the magnitude k and k plus dk between that. So v, which is this, divided by pi square k square dk. Okay, so v is basically Lx into Ly into Lz, and k square is basically square of the magnitude of the k value divided by pi square. Now what we want to do is that we want to convert this, instead of talking about in terms of k, I would like to bring this picture back into energy. Okay, so this corresponds to one energy, this corresponds to another energy. So I can say in this dE, how many number of electrons are there. So how can you bring this expression instead of k? We want to bring it in terms of E. So what we need to do is basically to use the relation between energy and the momentum, which is basically, but we know E is equal to, again, h cut square k square by 2m. So this relationship I can make use. So I can substitute for k square here. So therefore k square is basically 2me by h cut square. I can substitute that. Similarly, I can also substitute for dk. So what is dk? You take a derivative on both sides. So that will give you 2k dk is equal to 2m by h cut square. Then E, so differential of E is basically dE. Okay, and then I can write, therefore dk is equal to, so 2 I can cancel, I can write it as m by h cut square dE by k. But k I can substitute back. If k square is this, then k is basically 2me square root divided by h cut. So if I do that, then I get the expression for dk also. So m by h cut square, and k is what? Square root of 2m into e raised to half, then h cut. Okay, so did I put all the term m by h cut square, then square root of 2me by h cut into dE. Okay, so if I take okay, h cut square, one term I can cancel, and then m I can write it as m raised to half, divided by root 2 into h cut, into e raised to minus half into dE. So I can write dk like this, and also I can write k square like this. So these two things, if I substitute into this expression, what I will get basically g of e dE. So I will just, basically it is a variable transformation. K is changed to e, and v is a constant, so that remains by pi square. Then just substitute this 2me by h cut square into 2me by h cut square into m raised to half by root 2 h cut e raised to minus half into dE. This is just calculus rules. So now I can just rearrange these things. Rearrange this. If I rearrange, so what I can do is this root 2 I can cancel with this, and then I can write root 2 here. Then what else I can do? Okay, e and e raised to minus half I can combine as so I can just cut this and write this as e raised to half. Then what else? So m into m raised to half, that is m raised to 3 by 2. Okay, so let me just v by pi square, then there is root 2, then m raised to 3 by 2, then e raised, so that is square root of e into dE. Then there is there's an h cut here and h cut square here, so I can write h cut cube here. So this is what I get. So there is a bunch of constants, then square root of e and e. So that is how it comes. Now it is also, you can substitute for h cut as h by 2 pi, and then some cancellation with pi you can get. So if you do that, so let me just do that. V by pi square into h cube by 2 cube pi cube into root 2 m raised to 3 by 2 square root of e Okay, so this pi square will cancel with this, and then so 2 into 2 and a half, sorry, 2 into 2 raised to half, I will write it as 2 raised to 3 by 2, and then I will have a 4 there. So I will have a 4 pi, and then 2m the whole raised to 3 by 2 by h cube, by h cube, and then I have a v here, v into square root of e, then d. I think this is correct. Okay, so this is what is this? So let me just tell you what is this. This is the number of states between E and DE. So that's what we got, number of states between E and DE. So now if I want density of states, okay, so let me just write it this way itself, rather than writing G of E into D of E. So I will just remove this. Okay, you should understand what is it. This is number of states between K and K plus dk, and similarly I have now did a variable transformation from K to E by using this E-K relationship, and got number of states between okay, so number of states between E and D. So let's keep it like that. Let's not define. So now we can come to what is called as the density of states. So what is density of states? Density of states for free electron. So now we can write it as this number. Okay, let's say it is called n of e, some delta n of e. Okay, so delta n of e divided by dE divided by V. So this is how we define. So per unit energy per unit volume. Okay, so therefore so we can call it as D of E, that is D of E, density of states, is basically delta n of E, which is this. So when you divide by dE, it will go, V will also go, so we will get it as 4 pi by h cube. So this formula you have to by heart. Okay, square root of E into dE. So this is the density of states for free electron. Density of states for free electron. Now let's go to crystal. The same thing we can now talk about in a crystal. So what does this tells us? As the energy increases, you will have, for a unit energy, you will have more and more states available. At higher energy, you will have large number of states available compared to lower energy. So that's what it is. Okay. So in a 3D potential well, the electron states available increases with the energy of electron. So for higher energy electron, you have more options for electron to sit in different states. Increases with the energy of electron. the electron state available increases with the energy of the electron. Okay, so now let's go to the crystal. So density of states in a crystal. Now so when you talk about crystal, we know like the energy bands. When you introduce the periodic potential, we have the band formation that we talked about. Now to find the density of states, just like what are the allowed values of K. So K takes discrete values for a free electron in a, or it is not really free, it is a particle in a box, electron in a box. In that case, we have seen it is proportional to square root of E, density of states. But now so we need to again go back to our energy band structure. So if I redraw at least a few bands, so we have the bottom of the band like this. So this is the reduced zone, minus pi by a to plus pi by a, and this bottom now will be not 0, it will be somewhere right. And then you have the next band, which will be like this, and there is some gap in between. Again the third band will be after a gap like this. Okay, so now if you look at some of the portions, like for example yesterday I told you, if you focus on this bottom of this band, this particular band, the bottom of the band, you can approximate it like a parabola, and then we can define what is called as the effective mass and all. And if it is a parabolic relationship, then it has very similar EK relationship. Only difference is that instead of mass we have to use effective mass, and instead of this E starting from 0 for free electron, it will be starting at some EC. Let's say that this is EC, and then let's say, so if you are considering this band, that's bottom of the band, then you can approximate it as a parabola. And if you are considering the top of the band, another band, you can consider it with another parabola. So this parabola is going downward. So this we will call this point of energy where the top of the band is EV, the bottom of the E band is EC. So we are taking two bands. One is actually corresponding to an upward parabola, the other is corresponding to a downward parabola. So if you approximate it like this, then what we can say is that we can find the density of states in these regions. In these regions, that is where it is matching with the parabola, you can find the density of states by using the expression that we have already just derived. The free electron case, EK relationship was a parabola. So let me rewrite the EK relationship. So EK relationship for free electron is basically E is equal to h cut square k square by 2m. This is the mass of the electron here. So this is for free electron. Now EK relation for electron in a crystal. depending upon where the electron is, whether it is at the bottom of a band or at the top of a band. So let me say at the bottom of a band, bottom of a band. So if it is at the bottom of a band, then we can make use of an upward facing parabola and write this relationship as E is equal to EC plus h cut square k square by 2m star, 2m star. So there are two things coming here. One is the bottom of the band, energy of at the bottom of the band, energy at the bottom of the band is bottom of the band. And then second thing is this, it is not normal mass, it is effective mass, which we talked about yesterday. Effective mass at the bottom of the band. Okay, so now we can so this case, let us take first of all the bottom of the band case, and we can write basically E minus EC. So E minus EC, you can write it as h cut square k square by 2m star. So you can compare this equation 1 and equation 2. If you compare, if E is replaced with E minus EC and M is replaced with M star, we can make use of the earlier derived result for the case of crystal. So this is the insight, if we replace E with the E minus EC and M with the M star, we get D of E, density of states in a for crystal. So this is at the bottom of the band, can be obtained as, so what was our expression that we derived? So just make these two modification. So our expression is 4 pi by h square into 2m whole raised to 3 by 2 into square root of E. So E should be replaced with the E minus EC and M should be replaced with the M star. Okay, so let's do that. So we get density of states as 4 pi, and then we had a 2m, so that will be replaced with M star raised to 3 by 2. Okay, 3 by 2, and this divided by h cube, and then square root of E minus EC. So this will be the density of state in comparison with okay. So here I think I have put this DE should not be there. It should divide it by DE, so that DE should go away. V and DE should be going away after division. So this DE will be cancelled here, and V should also be cancelled. Okay, so this will be only this much. So that is the density of state at the bottom. Now let's look at what happens at the top of the band. So we are looking at a different region in the band structure. Okay, so now let's look at another case. Density of states at the top of the band. So the EK relationship for the top of the band can be written as, So this is also a parabola, but it is a downward facing parabola. Okay, so it's a downward facing parabola. So how can we write the equation for this? It is E is equal to EV minus some k square. So it can be written as E is equal to EV minus h cut square k square, because the parabola is now inverted, then by 2 m. Now yesterday I told you for the top of the band, okay, so this is for the top of the band. So this is an approximate way. So this energy at the top, EK relationship at the top, and write like this. So if I am using minus sign here, then I will take this m star to be the modulus of m. So m we got it as negative, right? So if I am taking m negative, then I have to put plus. But another way of taking is take a modulus here, and then keep the minus sign outside. Okay, so we derived this curvature is actually so the parabola is facing downward, the parabola is facing like this, so the curvature is negative. So m we yesterday found out 1 by m star was 1 by h cut square d square e by d k square. So this is what we found out, and so there we obtained it as a negative value. Okay, but I am taking that negative value as minus of modulus m star. That's the only thing I am doing. So we can write like this, which may be rewritten as EV minus E is equal to h cut square k square by 2 m star modulus. So this is at the top, so maybe I should put a suffix here for top, m star of the top, and here I will put bottom. So this is bottom, just to denote that it is top of the band and the bottom of the band. Okay, so this is top of the band. Okay, so now again I can name this equation as equation 3. Then comparing equation 1 with 3, what we can get is if you replace E with so 1 is what? 1 is this, E is equal to h cut square k square by 2m. If I replace E with EV minus E, and then m with m star t, then I have I can get the density of states as, so density of state for the top will be equal to, so I replace so we have this expression 4 pi into 2 m star, this is for top, so modulus, because we got it as negative, so I made it as a positive quantity, then divided by h cube into square root of EV minus E. Okay, so this is the density of states for the top of the band. Okay, this is the density of state for the top of the band, and similarly we got the density of states for the bottom of the band. Any question regarding this? Any questions? Is it clear? Density of states. What is density of states? What do you mean by it? Okay, so if it is clear, then we can plot these expressions. Density of state as a function of energy we can plot. So let's take energy in the y direction. So this is energy, and then d of E I will take in the so this is usually the way we plot density of states. So usually independent variables are taken in normal graph, we take in x-axis, and dependent variable on y-axis. But for plotting density of states, usually the convention is energy is taken in vertical direction, and the density of state is taken here. So there is some critical point. One is your EC. EC denotes the bottom of the band, bottom of one particular band, and then so let me just shift this line a little bit downward. So this is D of E. So we are considering just two band. The bottom of one band is EC, the top band is EC, and the top of the bottom band is EV. And if you look at this function, for example, if I want to plot this, you can see that this is a forbidden region. Between EV and EC, it is a forbidden region. There is no band here. So, and there is an energy gap here. So this is usually called as the forbidden energy gap, EG. And then as E is equal to EC, it is 0. Okay, when E is equal to EC, it is 0. But as energy increases, so the square root of a positive a quantity greater than EC, it keeps on increases, and it will be something like this. Okay, so it basically goes like this. And similarly, I can draw so maybe I will use this color. So this is basically this expression, plot of this expression. So as E increases above EC, it goes below EC, it is forbidden, so there is no states available there. So you see that as energy increases, you have a large number of states available. Similarly, you will have the plot of for the top of the band, top of the bottom band, like this. So okay, so it will be something like this. Now how much it is spreading, etc., it need not be symmetrical, because the effective mass for each band could be different. Okay, so it is going downward. Why? Because for energies lesser than EV, there only it has solutions. So therefore as you go downward, you will see that this is becoming more and more, inside the square root, EV minus E becomes bigger and bigger as energy goes down. As E reduces, EV minus E increases, right? So that is why it is spreading more and more. Okay, something like this. So this is the plot of the density of states for two particular bands. So we are considering two bands, and what we derived is that the density of states varies like this. Okay, so this we are going to use later in computing many things. Now let me quickly come to what is a semiconductor. So we have only talked about crystal and periodic potential and then energy band structure, but when can we say that a material is a semiconductor? A crystal could be a metal also, a crystal could be an insulator also. So under what condition we can say that uh, you know a particular crystal is a when is a crystal or when can we say that a crystal is a semiconductor? So that's the question I would like to consider. So question: when can we say a crystal is a semiconductor? So crystal means it has periodic potential and electrons moves in the periodic potential. So when can we say that a crystal is a semiconductor? The answer is by looking at the filling of the bands. So the answer is by looking at we can answer this by looking at, or it is not really the answer. The way we can answer is by looking at the filling of the bands. Okay. So this can be answered by looking at the way bands are occupied. So that is how we will answer this question. For example, so let's again draw the band. So without looking at the band structure, you can't say whether it's a semiconductor or a metal or what it is. Okay, so we had various bands like this. So this was our first band. Then on the top of that we had another band, and then again we had another band. So there is gaps in between, and then again we had another band. Now this exact variation, should it always vary like this? Not necessarily. So I will come into that maybe in tomorrow's class. So it can so these are the solution we got for like a simple 1D crystal. Okay, but in a 3D case the band could vary in some other ways also. Okay, it's not like from 0 to pi by a, either it is increasing or decreasing. You can have a maxima in between also. All these things are possible, but let us now look at just if this is the band structure, and then we have said that there are n states available. N is basically depending upon the so there are n states available, and all the states, suppose they are occupied. Okay, and then another band, all these things are occupied. Suppose if this is how the occupation of the bands happens. Okay, so now if this is the way the bands are going to be occupied, and let me also say that T is equal to 0 degree Kelvin. So that means there is absolute absolutely there is no thermal fluctuations or anything like that. So all the electrons will occupy the lower states, okay, because the electrons will be trying to occupy the lower energy states first, and then it will go to the higher energy states. Suppose the occupation, if this is the energy band structure and the electrons are occupied like this for a given material, then if you look at the next band, the top occupied band, we call it as the valence band. valence band. And that is why I took this as EV. Okay, the top of the valence band is V for valence, and the band which is just above the valence band is usually called as the conduction band. Okay, so this is called as the conduction band. Okay, so in a particular material that we are considering, so we have all the states in the valence band occupied and none of the states in the conduction band occupied. If this is the way electrons are filled up in a given band structure, then depending upon what is the spacing between EC and EV, so this is EC and this is EV, so this difference is what we call as the energy gap, EG. If your EG is if EG is greater than usually we say 3.5 electron volt. If EG is greater than 3.5 electron volt, we say the material is an insulator. Is an insulator. Now, if it is say between 3.5 and but greater than 0, EG is greater than 0 but less than 3.5, we call it as semiconductors. Then third thing is, if EG is equal to 0, we call it as metals or conductors. Let's call it as conductors. No, metals are conductors. Okay. So you have material can be insulator, semiconductor, conductor. Okay. So first of all, if something has to qualify to be a semiconductor, what is the thing? The energy band structure should be occupied. Energy band structure should be like, for a given energy band structure, the occupation of these states in all the states in the valence band, there is a top occupied band is called valence band. All the occupied states in the valence band, if it is fully occupied, and then at T equal to 0 degree Kelvin, there is no thermal excitation, so the above band will be completely unoccupied. Okay, in this scenario, if EG value is between 0 and 3.5, we call it as semiconductor. If it is above 3.5 electron volt, we call the material as insulator. And if EG is 0, okay, if EG is 0, so this is not the only way you can say conductor. There is another way, like or, so I should say the second option way in which we can have conductor is, or if a band is partially occupied. So alternatively, you can have conductors when a band is partially occupied. Then also it will be a conductor. So it is not necessary that all the states in the band is occupied, it is only partially occupied. Then also we say that it is a conductor. So conductor can be in two different ways. Either two bands are like touching each other, then we can have conductor, or you can say that one band is only half filled or partially filled. So that is also a case of conductor. But if it is a fully filled with an EG above, then it could be a insulator or a semiconductor. And why we say, so next question therefore, so this is how we say whether a material is semiconductor or a metal or conductor or insulator. Now why do we say so? Okay, so that's a more deeper question. why do we insist say that this is a semiconductor, or if it is like this is a conductor, etc. The reason is that as you go to the room temperature, okay, that is you increase the temperature to say 300 degree Kelvin, that is our room temperature, okay, which is also like 27 degrees Celsius. What will happen if it is a semiconductor? Few electrons, okay, in the valence band will get sufficient kinetic energy to cross the barrier and go to, or not only few, a considerable number of the order of 10 raised to 10 or more, can exactly, it will depend upon Eg value. So the probability, let me write, the probability of the electron to gain energy to go into the conduction band, probability of an electron in valence band to gain energy to go into the conduction band is proportional to e raised to minus Eg by kT. K is kBT, okay, kB is the Boltzmann constant. Boltzmann constant, and T is temperature in degree Kelvin. So this is the probability. So probability of electron getting an energy to go from the valence band to the conduction band is proportional to exponential e raised to Eg by kBT. Okay. Now at room temperature, what is kBT? kBT at room temperature. kBT at T equal to say 300 degree Kelvin is of the order of approximately 0.026 electron volt. You can so kB, if you know, it is 1.38 into 10 raised to I think 10 minus 23, right, joules per Kelvin. So if you multiply this thing with 300, we will get a very small number, but if you express that instead of joules in electron volt, you have to just divide it by 1.6 into, so the way we get this is you multiply 1.38 into 10 raised to minus 23 with 300, and then after multiplication you will get the energy in joules, which is very small. So what we do is we divide it by 1.6 into 10 raised to minus 19. So this many electron volt, that is 0.026. So if it is 0.026, then at room temperature, how many electron can go to the conduction band? So that is given by therefore e raised to minus Eg by 0.026. So this will be the probability. So this will be so this will be multiplied by some number. Okay, this is proportional to this, but if this Eg is like above 3.5, then at room temperatures you can say the number of electron going is like almost negligible. So that is why we say in conduction band negligible number of electron will be there in the insulator, because this number is going to be very small. Okay, so for insulator, so I said it is 3.5 or 4. So for insulator, Eg is around 4 electron volt. So e raised to minus 4 by 0.026. Okay, so this is very small. Okay, this is very small. Whereas semiconductor, uh, or semiconductor, if you calculate this, so this is like e raised to minus 1 by 0.026, that is moderate. Okay, it is moderate. And then if it is metal or conductor, e raised to, it is basically e raised to 0. This factor is almost 1. Okay, so that is like almost all electron like go, I mean any electron can go without at room temperature, all electron can go to the other band, which is like the same situation. High conduction. So this is high conduction. So if band is unfilled also or partially filled, then also it is the same situation, like you don't need any energy to occupy the further states. So conduction usually happen when you apply a potential. So when you apply a potential, the electron will try to go to higher energy. It will try to increase the energy. So if it has to increase the energy, it should be easily, higher energy state should be easily accessible. But if it is at like far apart, it is not accessible, then it cannot go to that higher energy state, and therefore it cannot conduct. Alright, so we will stop here. If you have any questions, you can ask. Otherwise, you can leave.
Sir,
Yes.
sir, in semiconductor, then how this switching of takes place, sir?
Yeah. So switching means from valence band to conduction band. How do they go? That's your question, right?
Yes,
Yeah.
yes,
So that's what I am saying. The thermal energy, average thermal energy is of the order of 0.026 electron volt. This is a statistical figure. Okay. So this is like the mean energy. This is the mean thermal energy per electron. Energy per electron. Now, if mean is this, means there are many electrons which have energy higher than this, and there are many electrons which has energy lower than this. Okay, so as you go away from the mean, then what happens? The number of electrons having those higher energy reduces and reduces. So, but still there will be some fraction of electron which will have energy, enough energy, that is say 1 electron volt, for example. So 0.026 electron volt is like the average or mean energy, but there are some electrons here and there which get energy once in a while, sufficient enough to cross the barrier. So those electrons only go to the higher band. Are you getting what I am saying?
sir.
Yeah. So this is called as thermal generation of carriers. The electrons are generated in the upper band because of the thermal excitation. And the fraction, for example, if you take silicon, this energy gap is around 1.1 electron volt. Okay, so that figure I can give you for silicon. So for silicon, Eg is equal to 1.1 electron volt, and the number of electrons in the upper band at T equal to 300 degree Kelvin, the number of electron in conduction band. Okay, so now you know what is conduction band. That is the upper band, which is unoccupied at T equal to 0, but higher temperature it will begin to occupy because of thermal excitation. Number of electrons in the conduction band, say N, is of the order of 1.5 into 10 raised to minus, sorry, not minus, 10 raised to 10, 1.5 into 10 raised to 10 per centimeter. So this is the number that you will get. Now this number will decide the conductivity of silicon at room temperature. Pure crystalline silicon conductivity is entirely determined by this number. So if you heat the silicon material, this number you can further increase, because you will make more and more electrons to thermally excited to go from conduction band to the valence band to the conduction band.